Okay, another, find the critical numbers. Let's find the derivative. So this derivative's not too bad, 2x. And then remember logarithms, 1 over the argument, derivative of the argument. 1 over argument, derivative argument. And so we got 2x plus 3 over 3x minus 6. You could simplify that fraction by dividing everybody by 3 if you wanted to. 2. Set equal to 0. So 2x plus 3 over 3x minus 6 equals 0. Clear the fractions. Clear fractions. So 3x minus 6, 3x minus 6, 3x minus 6. On this first one, I'm going to distribute. So I'm going to get 6x squared minus 12x equals 0. Solve this guy in your favorite way. And my favorite way here is going to be to factor. So 6x times x minus 2. It is now factored and equal to 0. And like we said before, factored equal to 0. You can split that up. Again, from the zero product theorem that says if two numbers multiplied to be 0, one of them has to be 0. And we get x equals 0, x equals 2. Now here was the correct way to do this. Now somebody here is going to factor, or is going to divide by x. And notice if you divided by x, that x would disappear and you would just get 2, which could lead to all sorts of problems. Do not divide by variables. When you divide by a variable, you're basically telling the world, I already know that that variable is not 0, because you will lose solutions of zeros. Do not divide by variables. And then where the derivative doesn't exist, my denominator, because I had a denominator there, so 3x minus 6 equals 0, 3x equals 6, x equal 2. And so there you go. And you type those answers into MyLab Math, and it's going to say that they are wrong. And so you check your arithmetic again. And they're going to still, you check all your arithmetic, and so you look at your derivative, and you say the derivative of x squared is certainly 2x. 1 over the argument, derivative of the argument. Then I set it equal to 0, multiplied by that. And that's 6x squared minus 12x. And I factored, and I don't find a mistake. I really don't find a mistake anywhere. That 2 crept up twice. But I still don't find a mistake. Why is it counting me wrong? Because I just ever so slightly said it. I wrote it down, but I didn't emphasize it. A number C in the domain. In the domain. And so let's make a note here after the fact. Note. The domain of f of x equal x squared plus the natural log of 3x minus 6. The domain here, because we can only do logs of positive numbers, the domain is what I get when the inside of my logarithm is positive, when it's greater than 0. Remember, domain are the numbers that you can use in your function. Domain are the numbers that you can substitute into your function and everything works out just fine. Your calculator will give you a nice real answer. And so my domain here is x greater than 2. Neither one of these numbers are in the domain. And so x equals 0, x equal 2, not in the domain. And so this has no critical numbers. Now, I'm not going to do this to you on a test or quiz and tell you to find, something like this. But I wanted to do it in homework because it does creep up every once in a while. That a number you legitimately calculate here doesn't turn out to be a critical number. And that is because of this domain issue, that the very fundamental definition of critical numbers is that it must be, the numbers themselves must be in the domain of the function. And so here my function was x squared plus the natural log of 3x minus 6. We're only doing logarithms of positive values, which then tells me my domain. And so my domain is x greater than 2. Well, neither one of the numbers I got were in the domain, so this guy has no critical numbers. And so that will creep up every once in a while. And if we look at a graph of this, and let's clear out the old stuff that I was doing. So we had x squared plus the natural log of 3x minus 6. And I'm just going to zoom 6 initially. So I don't get a great graph there. So let's do a little bit better thing. Now notice I don't get anything over here because notice we don't get anything until it starts at 2. That corresponds to my domain being x greater than 2. So I don't see any graph until the point till I get x equals 2. That corresponds to domain. Then let's hit my window here. And instead of starting at -10, I'm going to start at -1 so I can just see my axes. And, let's go to say, actually I'm going to start at -4. You'll see why in a minute. And let's go to 40. I'm going to count that off by 4s. And let's do the same thing here. -4, 40, count that off by 4s. And I only start at the negative so I can see the axes, and I'll hit graph there. And there's a prettier picture. And so we can somewhat assume that the graph's going to keep going on like this. Now the reason why I put up the graph, one of the things that we had earlier was this. All local extremes occur at critical numbers, but not all critical numbers yield local extremes. My graph has no local extremes. Therefore, the function could not have had critical numbers. No critical numbers, no local extremes. That is an important correlation that we wanted to make with this graph. One of the other things I wanted to say about this particular function. It had no critical numbers, which means I'm not going to see any local extremes. And certainly on the portion of the graph that I see, I don't. And you can just trust me that the graph essentially looks like that. So no critical numbers. So no local extremes. But one of the big points I want to make here, if for some reason you come up with numbers here, but the computer doesn't accept them, it's probably because of that domain issue. Okay, let's do another problem. Find the critical numbers. So same steps. 1, the derivative. So that's going to be, well, first of all, I'm going to rewrite that radical. Square root, same thing as exponent of 1/2. And so what I've got 4x minus 32x to the minus 1/2, which is 4x minus 32 over the square root of x. I prefer to see the fractions. 2, the derivative equal to 0. So 4x minus 32 over the square root of x equals 0. Clear that fraction. So multiply everybody by the square root of x. So I've got 4x times x to the 1/2 minus 32 equals 0. Just being very explicit with what I'm about to do. Add your exponents, and so that's going to be x to the 3/2 minus 32 equals 0. 4x to the 3/2 equals 32. X to the 3/2 equals 8. And x to the 3/2, use the reciprocal power, 2/3. 8 to the 2/3. And so I get x equals, that's the cube root of 8 squared. Remember, the denominator gives you the index, the numerator gives you the power. That's 2 squared, or 4. But there are two types of critical numbers. Where the derivative equals 0, we got that one. And then the second type, 3, where the derivative does not exist. And so I would take that square root of x equals 0, square both sides, and I get x equals 0. So 0 and 4, critical numbers. Okay, then what we're going to move on into this section for our last couple problems is starting to use these critical numbers. Like I said, we were moving towards doing very, very long problems where one step will be the critical numbers. Now, these aren't going to be incredibly long problems. They're going to be shorter problems, but we're moving to these incredibly long problems. But these guys are going to be shorter. So recall a couple facts here. Facts: if f of x is continuous on a closed interval, then f of x obtains both an absolute maximum and an absolute minimum. 2, absolute extremes occur at critical numbers, or in the case of closed intervals, at the endpoints. So keeping those two facts in mind, how to find absolute extremes on a closed interval. 1, find the derivative. 2, find the critical numbers on the given interval. Because we're only interested in what's happening on whatever interval we're talking about. 3, evaluate the original function at each critical number found and at each endpoint on the given interval. Original function because you're trying to find the absolute maximum minimum value of the original function. The derivative and the critical numbers are giving us locations to look at on the original. So we're going to do the evaluation to find the value in the original function. And then 4, identify the absolute maximum, absolute minimum. So I'll go on for this first problem, which we will do in the next video.